Here I'll be demonstrating how to build an HVAC system for your Project 1. In passive houses in the US, ducted or ductless mini splits are the most common type of system, and we can simulate those using the VRF objects in OpenStudio. I'm starting from the same model I used in the previous video for the DOAS system. And the first thing you'd want to do is make sure that your model is running with no severe errors and it's behaving as expected before proceeding. You want to ensure that you've got a weather file assigned, that you've got the design days imported, and also that you have your OpenStudio results measure loaded as well. You'll want to make sure that you've got outdoor air and infiltration objects defined for your spaces. And under the Simulation Settings tab, under Simulation Control, you'll want to make sure that Zone Sizing Calculation, System Sizing Calculation are both on. Those are the critical ones for this. I would go ahead and turn on Plant Sizing because you'll probably use it later. And I generally recommend leaving the Run Simulation for Sizing Periods turned off, but you do want to run it for the weather file run period. This is your run period up here. It's the dates for which it's going to run the simulation, and this button tells it to go ahead and do that. You'll also see that by default OpenStudio has a standard heating sizing factor of 1.25 and a cooling sizing factor of 1.15, which are pretty typical values to increase the size of the system over the load calculated based on the design conditions. So the first thing we'll do is we'll start with schedules. You may already have heating and cooling set points schedules defined, or thermostat schedules defined. However, you'll need to adjust them for the Passive House standards, which uses 68 degrees Fahrenheit for heating and 77 degrees Fahrenheit for cooling. So the most convenient thing to do is go ahead and display your model in IP units, if you haven't already, or convert from those values to SI. I'm going to start with my cooling set point schedule. Schedule type will be temperature. Apply that. I'm going to name it so I know what my schedule is. And my cooling set point is 77 degrees Fahrenheit, so I can just type in 77 return while hovering over the line, and it sets it there continuously. And note that I did that on the default schedule page. In practice, you would probably want to operate such a building with setbacks. Depending on your zones, you'll have multiple zones. So you might have zones when they're unoccupied, having a setback for cooling a higher temperature when the zone is unoccupied, and for heating a lower temperature when the zone is unoccupied. But for Passive House compliance, we just use a continuous heating and cooling set point. So that'll be our cooling set point. I'm going to create another new object down here, the green plus, to create my heating set point schedule. Again, it'll be temperature. I'll apply that. I'm going to name it some name that I can recognize, and then I'll hover over my line again, type 68 Fahrenheit, and there we have it. I'm also going to create one more schedule, which would be an availability schedule. We're not going to apply it right off the bat, but I just want to demonstrate how you would use it here. So for this, it would be an on-off schedule, and I'm going to apply that schedule type. I'm going to call it availability cooling. And in practice, most residential HVAC systems have to manually be turned over from heating to cooling mode and vice versa. And probably on the occasional winter day when it gets a little bit warm, most people aren't going to turn on their air conditioning, and vice versa during the summer. So here in this availability cooling schedule, 1 means on, 0 is going to mean off. Just because we start in January and end in December, it'll be most convenient if I start at 0. So I'm going to make my default value 0. And then under Run Period Profiles, I'm going to click the green plus, add a new one, click on that one, and that one's coming at 1. And I'm going to apply that from, let's say we turn it over on April 15th to cooling, and then we end our cooling phase on, let's call it October 15th. Applied every day of the week. And then in a little bit here, when we get to setting up the HVAC system itself, I'll explain where you would apply this if you were going to use that type of schedule. You could do the same thing for heating, but in reverse. Next, we're going to go to our Zones tab and apply our cooling and heating set point schedules. You may already have schedules applied here, in which case you would want to either modify those schedules or delete them. I'm going to browse over to My Model on the right, Rule Set Schedules, find the ones I just created. So I'm going to apply set point cooling to cooling. Here I've only got one other, but I'll just use the, oops, not that one. Use the shortcut method for applying it here. I'll do the same thing for heating. I'm going to browse in My Model again on the right under Rule Set Schedules, grab my heating set point schedule, select it, apply to selected. All right, I'm going to save my model with a new name now. And we're ready to start building our actual HVAC system. So I'm going to click here on the HVAC tab, square arrows that return on themselves. It'll take a little while to click over there. And then on the pull down on the upper right, first of all, here's my DOAS system that I built in the previous demonstration. I'm going to go down to VRF here. Now, before I go on though, there are many types of more conventional HVAC systems that I could build in this area. If I click the green plus, it's got systems that roughly correspond to the ASHRAE 90.1 standard systems, as well as some other things like hot water plant loops and so forth. There's a lot we can do here. But VRF systems are unique, and the main difference is that they're not loops of air circulation primarily, they're loops of refrigerant circulation, and so they're modeled a bit differently. So I'm going to pull down on VRF, come over here, and then under Library on my right hand side I'm going to browse down to VRF System. You'll probably just have one object choice in here. I'm going to drag the one called VRF System up into where it says drop VRF system, and it creates it. If I had multiple different VRF systems in the model, then I could drag more over here into this box and keep creating more. But in ours, we're going to assume that we've got one outdoor unit with multiple indoor units, because that's part of the standard practice of the way this type of system is applied, and part of the beauty of its efficiency is that you can create multiple interior zones with relatively low loads on one outdoor condensing and evaporating heat pump unit. So if I actually, first thing I did there was let me go back. I'm going to click on the magnifying glass here to expand that system. And then I'll see the actual unit, and I'm going to click on my system object over here and look at my settings here on the right. If I had multiple systems, I'd want to go ahead and name it, but since I'm only going to have one in this model, I don't need to do that. My availability schedule is set to always on, and that's fine. That's typically what you're going to want. And by default, it's going to come in as an auto-sized object. Once you got further down in a project where you actually knew unit sizes, you'd go in and hard size it here. But for what we're doing, auto-sizing it is the way to go. Probably the most important setting here to get right to reflect the actual performance of the system that you want to look at is the heating and cooling COPs, or coefficients of performance. On box in the distributed folder in the calculator section, I've put an Excel spreadsheet which has a calculator that will allow you to convert from SEER values and HSPF values to the COP. So SEER stands for Seasonal Energy Efficiency Rating. HSPF is Heating Season Performance Factor. And they use somewhat different but similar methodologies to try to come up with an overall efficiency rating of various different HVAC systems. SEER is for small residential sized air conditioning systems. It's the cooling side of the equation. HSPF is for smaller residential sized heat pumps, which would be the heating component of this type of system typically. Values that you see filled in here are reasonably commercially available, efficient, reflective of reasonably commercially available, effective equipment and efficient equipment. And those are the ones I'm going to use in the demonstration here. You could potentially go a little bit higher. You probably wouldn't want to go a whole lot lower since we're trying to create a really high performance building here. We need to use high performance equipment as well. Just for reference, the minimum allowable SEER value by code is 14. So a SEER of 22 is a very efficient air conditioning system. So the COP for that is going to be 4.38. On the heating side, when we get down there, it's going to be 3.69. And COP is just a ratio of the energy in to the heat supplied or heat removed by the system. So we're actually saying for every 1 unit of electricity in, we're removing, in the cooling side, 4.38 units of heat from the building. And that's because we can see what appears to be a greater than 100% efficiency because we're using a refrigeration system to pump heat rather than just provide heat directly. So I'm going to, over here, enter my COP value. We can leave most of the rest of these settings at their defaults. You'll see that there are a very large number of performance curves and related performance values that have to get defined here, which are built into the default system here. Again, on the heating capacity down below this section of pull downs, we're going to allow that to auto size, and we want to adjust the heating COP as well. And I'm using in the example here 3.69 for that COP. Another important value to check, which looks fine in the defaults here, is the minimum outdoor temperature and heating mode. -4 Fahrenheit is a pretty typical value. Some can go even lower than that. But it's actually, what this is saying is that this system is still capable of operating in heat pump mode even when the temperature is 4 degrees below 0 Fahrenheit. It's still going to be able to extract heat from the outdoor air to provide to the interior. Scrolling down a bit more, you're going to want to set the zone name for the master thermostat location. This is going to be the thermostat that controls the decisions to operate in heating or cooling mode. And I'm going to, in my model, make that thermal zone 1, but it could be whichever zone in your model you feel like should get priority. Another important one to look at is heat pump waste heat recovery. This is a capability that some VRF systems have, especially larger, more commercial type ones, but some smaller residential ones do as well, to actually shift heat between zones in the case where you have one zone calling for heating while another is calling for cooling. It can pump the heat from the zone that needs cooling to the zone that needs heating, and you get essentially near-free space conditioning using that kind of methodology rather than running the compressor in order to pump that heat in, and also better comfort. You in a small building like this, you may not have that kind of differential situation, so it might not end up doing any good, but we're going to go ahead and leave on the waste heat recovery. So I'm going to turn that to yes here. Otherwise, we can leave the rest of these settings at their defaults. It's going to auto-size the things like the backup heating coil and so forth. All right, I'm going to go back to my library tab. Now browse up to VRF terminal. I'm going to select the VRF zone terminal object and come over and drop it on here. So this is going to be our first indoor unit. And this could be reflective of a wall-mounted mini-split type system, a ducted mini-split, ceiling cassette, many different types of equipment. The fine points of those different types of equipment would involve fan pressure rises that would result from the addition of ducts and so forth. The most common situation in passive houses is probably the wall-mounted versions, and so we can kind of gloss over some of those fine details for what we're doing here. So I'm going to click on this indoor unit, and I'll see its parameters pop up here on the right side. So we want to go ahead and set up this one first so that we can copy its properties over to the other ones as well. So again, we're going to leave the availability schedule for the entire unit to always on. We want all the supply airflow values to be auto-sized. Again, we don't know exactly how much airflow capacity is needed to condition the space yet, so we're going to let it auto-size those values. For all the outdoor air values, we're going to hard size those at 0, and that's because we have the separate dedicated outdoor air system. So none of the outdoor air is coming in directly through this VRF system. That's not necessarily the case. You could have a VRF system that used that had outdoor air connected directly to it, but we have the dedicated system that we already modeled, so we're going to set all those to 0. If I come on down to my fan section, again, I'm going to let it auto-size the fan. Come on down to the cooling section, a little bit further down, past all the coefficients for the performance curves. Again, I'm going to let it auto-size. I'll let all these values auto-size. And this is where I could apply my availability schedule that I set up earlier here. Well, I'm actually not seeing it right. Oh, there we go. Availability cooling. I'm not going to do that right now, but this is where I would set it in order to limit the availability of cooling to a certain time frame. And then if I come on down and look at the heating coil here, same idea. I could set an availability schedule if I desired on this one. And again, I'm going to let it auto-size these values. For all these auto-sized values in an actual project once you got down to an actual design. You would probably want to come back in and hard size these, reflecting the actual equipment being used. I'm going to go back to my model now, grab my first thermal zone, call it thermal zone 1. I'm going to drop it over here on the thermal zone. And so now I've placed this piece of this indoor unit in thermal zone 1, so it's got a location. And one thing that I actually forgot to do over here, I'm going to go back and do it, is I definitely want to name my indoor unit something recognizable so I know where it is. It's going to, in the variable report, it's going to just call it this name, VRF zone terminal, and then it'll start adding numbers, but they won't necessarily align with your zones unless you manually name it. So I'm going to call it something distinct that I can recognize. Go back to my model again. So now that we've set all the values on this indoor unit, if we don't go in and add another indoor unit directly, but we just drag in our next thermal zone, it'll copy the same indoor unit. And you can see that it couldn't name it zone 1 again, so it increased the value by 1, so it named it zone 2, but I could go ahead and name this whatever I call that zone, if it was bedroom or living space or whatever I wanted to call it. And it's got all the same values defined. So you can see that it's hard sizing the outdoor airflow here, for example. If I had a different indoor unit, I could drop a new terminal on there and set it up separately. All right, I've got my model almost set up here. I'm going to save it. I'm going to come down to the Variables tab and turn on a few different variables that'll help us see what's going on here. There's obviously an enormous array. I'm just going to pick a few particular ones that I want to look at. So I'm going to turn on the site outdoor air temperature. Find it here. Site outdoor air dry bulb temperature. I'm going to turn on the zone air temperature. I'll leave this on hourly. I'm going to scroll down, find my zone VRF terminal total cooling rate. Zone VRF air terminal total cooling rate. I can also get the value in energy, but I'm going to look at it in terms of the rate, so we can see a progression throughout the day. And I want the total rather than the sensible or latent because I'd like to see the entire amount it's cooling. I can look at those separately as well, if so desired. Same thing for the heating. I'm going to get its heating rate, and then I'm going to ask for the zone windows total heat gain rate as well. So I can look at the impact of solar gain here. Save the model one more time, come over to run my simulation, and I'll wait just a moment for this to process. All right, so it's completed. Let's look at our output. I'm going to go ahead and focus on detailed variable data. I'll display it in IP units. That's all right. All right, so we're presently seeing our site outdoor air dry bulb temperature. the zone air temperature, and we can see, all right, it's largely behaving as expected. The indoor conditions are falling within this band here that looks a lot like our thermostat set points, although they don't match exactly. Same for zone 2. Let's zoom in on that. And we can see these characteristic clipped kind of temperature profiles where for most of the day it's getting pegged right at the thermostat set point, but we can see there's a little period on a lot of these days where the value bumps up. And I think probably what's happening is that we've got some internal loads in there that come on, and we've got the system that's kind of maxed out up to this point. The internal loads kick on, and for the next hour the system has to catch up and take care of those, and the temperature drifts up a little bit. So those would be considered unmet hours, and looks like we might have enough of them that in a project where we were going for LEED certification or something like that, we'd need to get that resolved because you can only have a limited number of unmet hours showing in your simulation for that kind of context for the ASHRAE 90.1 protocol. But we're not doing that here. That doesn't look like a significant issue, so we'll kind of ignore that. Looks like thermal zone 2 isn't experiencing any of that either. It just looks like it's our living space, which is, we're seeing some temperature spikes in. So let's look at our, first of all, let's take zone 1 and look at cooling, and we see, as we'd expect, that our cooling load is distributed primarily during the summer, but we do also have some cooling values spiking over here during the winter. And this is the kind of thing that we could take care of with that availability schedule if we said, okay, we're going to limit the availability of cooling to be, say, from April to mid-late October, something like that. We'd see all these go away. Let's look at our cooling in thermal zone 2. We have lower internal loads, so we're actually only seeing cooling during the summer in that zone, and we have some unoccupied periods with these schedules that I've used so that we're not even seeing constant cooling. We're even seeing a whole time period here when it's not calling for any cooling in that space. That's more an anomaly of the schedules being used than of anything more significant than that. Heating, distributed primarily in the winter, and kind of a similar profile. And then let's look at our cooling and see how that compares to our heat gain through windows in thermal zone 1 here. So during the winter, it looks like we can see some relationships. Let's look at the outdoor air dry bulb temperature as well. We'll put it on here, and we'll see. Let's see if we can tell on these times when the cooling loads really spike, for example. We have maybe higher than normal solar. We've had a couple of warm days here. We can see period where the outdoor air dry bulb has gone up the day before, so the building is now storing more heat. The next day it goes up even more. We see that cooling load really starting to spike, which is primarily a factor of both the stored heat from the day before, another hot day, a little bit more solar than some other days, but not an exceptionally high level, and then probably some internal loads that are coming on during that day as well. And here we see kind of a similar pattern. We've got a little bit of a warm spell. We see some cooling loads that are higher, but not really anything exceptional about solar gain. So that doesn't look like it's the reason for these cooling loads. And we could go in and delve in and figure out exactly why that's happening. But you can see the regular cadence of it is indicative of a recurring internal load that's occurring on a regular schedule here, it looks like. Okay, well, that's been an overview of how to create ducted and ductless mini split systems using the VRF objects in OpenStudio. These types of objects can be created very, very quickly. They're the easiest type of HVAC to model. And you can always, to get a model up and running and test it quickly, you can always create one of these systems, attach it to zones, and not spend a lot of time going back through and setting all of the detailed parameters right off the bat, so that you have something to test early on. But these are applicable to both small buildings and large. More and more large buildings are using VRF type systems as well. Even very large high-rise office buildings these days are using this type of system. So they're highly efficient and highly flexible. And OpenStudio has a capability to create these pretty effectively, and that's a unique quality to Energy Plus and OpenStudio compared to many other simulation tools out there. All right, so that concludes our video.